Hi everyone, my name is Ohad. I'm a student at the Yaron Bromberg's group at the Hebrew University. And in this talk, I'm going to describe our recent work on real-time shaping of entangled photons by classical control and feedback. Well, in recent years, many quantum technologies involving entangled photons have been demonstrated. And for example, you can think about quantum K distribution. But although really huge progress has been made, still real-world applications are slightly held back due to some practical challenges. In this talk, I'm going to focus on one main challenge, which is the optical link, and more specifically, scattering in the optical link. In the illustration here, you can see the Chinese satellite launched a few years back, which enables quantum K distribution and entanglement distribution for over 1,200 kilometers. And indeed, one of the main challenges that they faced is that scattering induced by the atmosphere, turbulence in the atmosphere, limited their performance. So the motivation of our work was to find a solution to compensate the scattering of entangled photons, for example, by turbulence in the atmosphere. Before diving into the details, let me briefly discuss how we create entangled photons and specifically spatially entangled photons. We use the very well-known process called spontaneous parametric time conversion, or SPDC in short, in which a classical laser that we call a pump beam illuminates a nonlinear crystal, and with a very low probability, a photon from the pump beam is being annihilated, creating two new photons, which we call the signal and idle photons. Of course, we have energy conservation so that the energy of the pump photon is divided to the signal and idle photons. Signal and idle photons can be emitted at various angles, so that if we look at the far field and scan with a single photon detectors or use a sensitive camera, we will get what we call the single photon counts, and they will exhibit a large spot corresponding to the large emission angle of the SPDC process. However, if we now look at the correlations between the photons, and we take one stationary detector and let the other one scan, and we only record the coincidence events, we'll get a much narrower spot. This is because, although the photons can be emitted at various angles, due to transverse momentum conservation, if we measure one of the photons, say the idle photon, at a specific location, the signal photon must have been emitted at the opposite direction. This is exactly why we call the photons spatially entangled photons. They begin at a very large superposition of angles, but once we measure one of the photons, the other collapses to a well-defined position. However, if we now add scattering media, for example, a diffuser in our case, or a turbulent atmosphere, we get that the nice correlations between the photons are scrambled. If I now measure one photon at a specific location, its per photon collapses to what we call a two-photon speckle pattern. So our goal will be to try and recover the delta correlations between the photons. Can we go from this speckle pattern back to a well-localized spot? It's important to note that this is possible because what happens here is not decoherence. Yes, the entanglement between the photons is scrambled, but this is in principle a reversible process. This problem was discussed in various research in the past few years, where people have developed methods to shape and control single and entangled photons in order to compensate the scattering. However, although really huge progress has been made, real-time shaping, which is required for any practical application, was not demonstrated for entangled photons. So let's think for a minute about how can we compensate the scattering of entangled photons. The most naive and direct approach will be using the following setup. We can create entangled photons and use a spatial light modulator or an SLM, which is a device that helps us tailor the phases and wavefront of the incoming photons to try and compensate the scattering induced by the diffuser. So we shape the phases of the entangled photons using the SLM. We use the correlations between the photons, which is what we want to optimize as feedback for some optimization algorithm, and we try to recover the delta correlations we had before. However, this approach, although being very intuitive, has two main drawbacks. The first The shaping process using the SLM or any other device adds loss to the quantum link, which is of course something we want to avoid. The second problem, which is much more important, is that by using the feedback from the quantum signal, we'll get a very slow optimization. This is because the quantum signals are inherently low, especially after scattering, so that the signal-to-noise ratio will be quite bad, and we need very long integration time in order to perform the optimization. This was overcome in recent experiments by using an additional laser with the same wavelength of the photons, performing the optimization in advance, and then performing the experiment. However, this requires to put back and remove this additional laser, which is not practical outside of the lab. So, what is our approach? We do two main things differently. The first is that we move the SLM and put the spatial light modulator on the pump beam. Therefore, instead of shaping directly the entangled photons, we shape the pump beam that generates them. The question here is, why would shaping of the pump even work? What I really want to optimize is the entangled photons, not the pump beam, right? And the answer for that was given by Munken over 20 years ago, which shows that anything you put on the pump beam, any manipulation you do on the pump beam, for example, here you see the mask with the letter C, the same will be observed in the correlations between the photons. This is what is called the transfer of angular spectrum in SPDC. So now we know that every shaping we do to the pump beam will be transferred to the entangled photons. So we can, instead of directly shaping the entangled photons, we can shape the pump beam that generates them so that the photons are already created with the desired correlations to compensate for the scattering. So we solved the first problem by now removing the spatial light modulator from the quantum link. However, the process will still be slow because we are still relying on the quantum signal for the optimization. So the second thing that we do is that we let the pump beam propagate together with the entangled photons and scatter by the same scattering medium. Then we separate the pump beam using the dichroic mirror and measure it with the camera. If we ignore for a minute from the nonlinear crystal, what we have here is a classical laser shaped by spatial light modulator, scattered by a diffuser, and measured using a camera. And the intensity of the pump beam is used as feedback. This is a classical wavefront shaping scheme and can be done in real time because the classical pump beam is a strong laser. But the question here is, why would pump feedback even work? I mean, what we really want to optimize is the correlations between the photons. Why would feedback provided by intensity of the pump beam will do the trick? And we know that scattering of different wavelengths for classical light exhibit strikingly different spectral patterns. For example, here you can see the picture of the spectral patterns observed when illuminating a scattering sample with white light. And you can see indeed that different spectral patterns are observed for different colors. This is because the scattering of the optical waves is highly dependent on wavelength. However, as we discussed before, for the entangled photons at 800 nanometers, we look at the correlations. However, for the pump beam at 400 nanometers, what we look for is the intensity. And it turns out that these two differences actually cancel each other, and that for quantum light, in our case, the two entangled photons at the wavelength of 800 nanometers actually act as one photon at the wavelength of 400 nanometers. To convince you this is true, we can look on the spectral patterns observed after the scattering. So these are experimental results. On the left, you can see the spectral pattern observed on the camera with the classical pump beam, the intensity of the classical pump beam. This picture is obtained with an exposure time on the order of microseconds, while on the right, you can see the correlations and coincidence rate measured between the two single photon detectors, raster scanning each point and point, and such measurement takes hours. And you can see that there's a striking similarity between the two patterns. The only difference is that the coincidence pattern for 800 nanometers, because of the different wavelengths, is stretched by a factor of 2. So what we get from here is that due to this remarkable correspondence between the pump beam and the entangled photons, we can simply measure the intensity of the pump beam instead of using the very low quantum sigmas. Going back to our experimental setup, what we have is we pump the nonlinear crystal using a pump beam which is shaped using a special light modulator. Both the pumping and the entangled photons are scattered through the same diffuser. We separate the pumping and use its intensity as feedback for the optimization algorithm, and we measure the correlations between the photons. So here are the results. We take the pumping, we perform the optimization, finding the correct phase mask to put on the SLM so that we get a nice optimized spot, and simultaneously with the exact same phase pattern, we get that the quantum correlations are enhanced and localized as well. So this establishes a nice correspondence between the shaping of the pumping and the shaping of the entangled photons, allowing us to rely on the feedback from the pumping. The use of the feedback from the pumping allows us to perform real-time or on-the-fly optimization. What we do now is that we put our diffuser in the setup on a moving stage, producing a time-dependent spectral pattern as would it be for practical applications, for example, in the atmosphere. So on the x-axis, we have the time, and on the y, we have the signals for the pump coincidence rates. You see in blue that although the diffuser is constantly moving, we can optimize the intensity of the pumping, and in red, the coincidence rate follows the same curve. So we are able to simultaneously optimize the pumping and the coincidence rate. And of course, after we turn the optimization off, because the diffuser keeps moving, we get this decay. For comparison, if we use the exact same algorithm and parameters and just switch the feedback to be the coincidence rate, we get no enhancement whatsoever because of the weak signals. Next, after we showed experimentally that our method works for real-time optimization and stationary optimization, we would like to show the relation for practical applications, for example, atmospheric turbulent links. So we simulate using Kolmogorov's theory of turbulence, a quantum link between the transmitter and receiver through turbulent atmosphere. What we show here is the link efficiency as a function of link length in log scale. And we do so, we simulate the results for 3 different turbulence conditions. And I want to stress that the simulation is performed with practical parameters. For example, we include dispersion here. You can see in dots that for the different turbulent conditions, there is quite a fast decay of the efficiency of the link with length, and optimization allows a significant improvement of the link. For example, if we look at moderate turbulence in green, you see that for 1 kilometer link, we get a link efficiency of 90% with optimization and almost 0 without optimization. Alternatively, you can say, I want to get a link with 50% efficiency, and there's approximately 2 orders of magnitude improvement in the link, achievable link length. So to sum up, both the shaping and feedback in our case are provided by the pumping using this nice correspondence between the scattering of the pump photons and the entangled photons. This opens the door for real-time shaping. I didn't have time to show you, but we get the same efficiency as in classical reference shaping. I discussed the relevance for phase-space quantum links and lossy media, which we also didn't have time to discuss, but you can find everything in the papers. And if you have any questions, you can contact me. I want to thank Yaron Bromberg, my advisor, and Gior Hassan, who worked with me on this project, and of course, the funding agency. And thank you very much.